Welcome to the TechArena, featuring authentic discussions between tech's leading innovators and our host, Allyson Klein. Now, let's step into the arena.
Welcome to the TechArena. My name is Allyson Klein, and we're recording this week from OCP Lisbon. And it's been a fantastic week already. I'm so excited to have Nilesh Shah on the show, VP of Business Development at ZeroPoint Technologies. Welcome to the show, Nilesh. How's it going?
It's going great, thanks.
Now, I feel like you and I have been circling the globe together. I saw you at Chiplet Summit, I saw you at GTC, and here we are in Lisbon at OCP. Why don't you just provide some background on ZeroPoint Technologies, since this is the first time the company's on the show, and your role at the company?
Absolutely. I'll give you a brief background on the company. So ZeroPoint, and it's, we are at OCP in Europe. So ZeroPoint is actually a startup based out of Sweden. It was founded back in 2016. Came out of the Chalmers University out of Sweden, and it was founded by Per Stenström, who's pretty well known in the computer architecture circles. And they've been researching compression algorithms for several years. And that's where the company sprung out of, got some initial funding, and then since then had a couple of other rounds of funding. The company is primarily focused on data compression. So what they figured out is, of course, there's an explosion of data, the data centers and devices and whatnot. But what they figured out is 75% of the data is redundant or can be compressed in some way. So that's the focus of the company. So ZeroPoint is an IP licensing company. We develop hardware IP components primarily focused on compression across the memory hierarchy, starting from cache compression all the way down to flash compression, and then everything in between, CXL, main memory, and so on and so forth.
You know what you're talking about? There's always been a value in compression, but when you consider the amount of data analysis and data movement in the AI era, you can start really seeing why this technology would have a lot of value for a lot of people. And what attracted me to talk to ZeroPoint is just the fact that we are entering the chiplet economy, and a company like ZeroPoint has such a huge market opportunity within the open chiplet space. You're giving a talk this week in Lisbon on chiplet-based LLC cache and memory expansion. I get asked about this topic all the time from different clients about AI requirements for memory and really pushing memory capabilities. Let's just back up a bit and discuss, why is there this inherent problem with system memory for today's workloads?
That's a great question. So, of course, right now, if you look at all the noise around AI, and it's not just noise, it's actual deployments and investments following it. So there's several reasons for the way these new types of workloads have evolved. So let's just start with LLM, large language model. That's a great and popular workload that a lot of people are familiar with. So if you just look at LLMs and the need for, if you interacted with applications like ChatGPT, etc., it's all about responsiveness. So when you need this kind of responsiveness, there's actually a lot of work that went in before that to train these humongous models. And then when you're interacting with them, you need to run them in real time. The components of these models, there's weights, there's parameters, and several other things that go around this model. And where do they need to be stored? So it's memory. And then these accelerators like GPUs, that's the primary poster child for AI is the GPU. And so GPUs go hand in hand with HBM, high bandwidth memory. And one of the main reasons for that is you need to keep these compute engines busy all the time. So that's where you get your responsiveness and performance. So of course, the closer the memory is to the compute unit, and the higher the bandwidth and lower the latency, that's what actually differentiates you. So this is in contrast to, let's say, a CPU-based architecture where you had multiple levels of memory hierarchies. Maybe you have an L1 cache, an L2 cache, and L3, and then you went out to DRAM, and then you went out to an SSD. So you have these multiple layers, but in these AI type of workloads, what you need is a lot of memory, very fast at high throughput, and it has to be predictable. So when you look at your normal CPU architectures, a lot of out of order processing that occurs. There's a lot of variability in your responsiveness. With some of these accelerators, GPUs, and even if you look at some of the custom chips that the industry is developing, look at architectures like Grok or Tenstorrent, a lot of emphasis on predictable performance, and that's driving the need for on-chip memories. When we talk about on-chip memories, we're talking SRAM, and then the next level down is maybe HBM memory. So of course, HBM is the poster child of Chiplet done right. They required a lot of work and the JEDEC standards and etc. to be hardened. But so these are the workloads driving the need for memory in a chiplet format, so you can assemble them rapidly, high bandwidth, and then actually with the performance that's required.
You just killed my memory storage hierarchy pyramid, Nilesh, with what you just talked about. I'm going to mourn it for a little while. But, HBM, great example of 2.5D and 3D packaging technologies, bringing that core capability on die and delivering a different way that you can actually couple memory with logic. Take me back into why this sets us up perfectly for chiplet architectures, and where do you see this going?
Yeah. By the way, so when I think of HBM and when you think of the memory hierarchy, so AI is you can segment it into there's AI training, but that's just one piece of it. Then the next piece of it down from the training what the industry calls foundational models, right? Training models from scratch. So that's one area. The second area is then fine tuning. So that's where so maybe in the foundational model training space, there's a handful of companies, the multi-billion-dollar companies that are in that space. Then you have the fine-tuning space where you can take some of these foundational models and then fine-tune them for your business needs. So out there you have a lot more opportunity for the memory hierarchy coming into the play. And then you've made all these investments in these large clusters of HBM-based memory deployments. But now you need to recoup that at some point. So how do you recoup all this investment? Well, that's when you actually do inference and deliver some meaningful results that you can monetize. And when you're looking at those inference use cases, now the memory hierarchy becomes pretty critical in terms of delivering performance at a reasonable TCO, right? Total cost of ownership. So no, the memory hierarchy doesn't go away. It's just the different stages of these workloads.
Now, we are at the dawn of what we could consider an open chiplet era. A couple years ago, we saw the UCIe specification come out that enabled open interconnects for chiplets. How do you see this industry evolving, and why is memory such an important part of the equation in terms of full chiplet designs?
Yeah, if you look at so two parts to this question. One is the chiplet industry in general, and why memory for chiplets. So one thing about memory is when we talk about if you look at how memory is scaling. So let's take a look at SRAM memory specifically. If you looked at some of the data put out by all of the large fab manufacturers, the TSMCs and Intels of the world, if you look at as they shrink the process down, going down to 7 to 5 to 3 nanometers, the logic is scaling really well. So it scales as you would expect. You shrink the process node, everything shrinks well. But the SRAM is not scaling as you would expect it. So that's where you run into challenges. So if you take a look at your monolithic ASIC design, where you design everything on a single process node, I/O and memory and processing, that worked well until we got to these really small nodes. And now you're running into the challenge where memory is not scaling, so it doesn't make sense to pack everything into the same process node. That's where chiplets come into play, where I may want to have my compute die on a different process node, say 2 nanometer, but then maybe I want my memory on some other process. So I can package them separately, and the chiplet is a great way to do it, to split up the functionality. And maybe I want my I/O package separately. So that's where this interplay of chiplets and memories becomes almost kind of a natural.
What are the impediments today that you see to move forward with chiplets? And what do you see from the ecosystem that gives you a lot of optimism?
Yeah, if you look at chiplets, and we spoke about the chiplet summit, and there's a lot of industry standards that have developed. But let's first start with what's preventing chiplets from just exploding today. So you spoke earlier about interconnect technologies and standards like UCIe. So they solve the challenge of connecting two chiplets together. But that's just step one. So now you've connected these two chiplets together, but there's a lot of other things that need to be standardized. For example, let's take HBM, which is a successful example of a very specific instantiation of a chiplet. It's very well defined. There's a JEDEC standard around it, how to package it, form factor, etc. But with chiplets, when you define the interconnect, let's say UCIe, or you're at LCP, there's a bunch of wire protocol, and there's several other alternatives to just link two chiplets together. That's great, but that's step one. Now, the next step is how do these two chiplets talk to each other, because they may be running completely separate protocols on these chiplets, maybe like a AXI interconnect on one, or that may be the system interconnect. So now you need to get these chiplets talking together. You need to be able to test them in a common framework. You need tools if you're using different processes. So all of these are things that need to come together for the chiplet economy to really boom and bustle. Now, what gives me hope is when you look around at the standards that are developing and putting effort and the investment, right? It's one thing to build standards, but then you look at the number of companies investing time, effort, and energy to actually put out these chiplets. I think that's the most positive sign of the demand. And clearly the biggest value proposition of chiplets is the ability to improve your yield and lower your total cost. And not just cost in terms of dollars, but also time to market. If I want to put together a solution, let's say for the automotive market, I might have a low-end car, a mid-range car, and a high-end car. And in all of these, I may have different levels of functionality. So that is actually the poster child for the chiplet economy, where with chiplets, you can actually mix and match these different capabilities you need and get to market very rapidly. Now, I see the same thing being driven in the data center and the server use cases as well. So I think that's where the industry is making the push to broaden the impact of chiplets and this cost benefit beyond just certain vertical markets.
Now, you are the VP of Business Development for ZeroPoint. How does your company plan to disrupt in this arena?
Yeah, I'd love to chat about that. So ZeroPoint Technologies, like I mentioned, we have algorithms. So one of the key innovations of ZeroPoint Technologies is a cache line granularity compression algorithm that actually works at a single 64-byte cache line. Now, if you look at some of the industry standard algorithms, and there are several wonderful algorithms that work great for storage technology, Z standard, and so on and so forth. So these work great when you're working with big chunks of data, like a page or a block, or maybe even files. There's a lot of applications where you need to compress an entire file. But when you're talking about memory, you don't have enough time. You don't have seconds or milliseconds. No, you don't even have microseconds. You have nanoseconds. If you're going to do anything, you have a few nanoseconds to be done with it. And that's the technology that ZeroPoint has developed, is a cache line granularity algorithm, which operates in a few nanoseconds. and compresses and decompresses on the fly.
That's incredible.
So that's what enables us to integrate ourselves even at like an L3 or system level cache on the chip, and then even going out to CXL memory, which is still memory. It's of course SRAM is much faster, but the same technology can be applied to CXL and other memories. And so essentially our job is to get all of the way. We want to do compression and decompression, but we want to be invisible, and that's where ZeroPoint is really disrupting the industry by helping deliver the solution. And if you talk about chiplets, the value proposition of chiplets is cost reduction. And if you are going to cost reduce, but then you are going to build a chiplet, you have added some other components like IO and other things out there. So you want to amortize that cost more effectively. And what better way, if you're going to make a chiplet memory, the best way or one of the ways you could amortize cost is compress that by 2 to 4x. And so now all of your development cost has been amortized over this 2 to 4x memory capacity versus just the amount of physical space. So instead of having 4x the physical space, now you have the same effective capacity but with the same physical space.
That's incredible, and I'm sure some of our listeners are quite interested in what you just said and would like to learn more. Where would you send them for more information?
For more information, of course, if folks happen to be at ZeroPoint, is pretty much at all of the industry standard events, the future of memory and storage, and then the CXL events, the CXL DevCons. We have several other places where we are presenting. We're at pretty much all the standards bodies like OCP and SNIA, JEDEC, CXL Consortium. So these are great places to interact. Of course, there's a website. We have a newsletter that you can sign up for, so you can stay tuned. We have our LinkedIn site. You can connect onto our LinkedIn page. And then, of course, feel free to get in touch with me. And happy to chat with. I love chatting with people, especially about solving these problems for chiplets and data center and even devices. We play in all these domains. So yeah, I would love to feel free to reach out to me directly as well.
Thank you so much, Nilesh, for taking some time out of your schedule. I know that you're teaching here, you're talking to folks. It was great having you on the TechArena.
Thanks, Allyson. It was great to connect with you.
Thanks for joining the TechArena. Subscribe and engage at our website, thetecharena.net. All content is copyright by the TechArena.